In this video, we introduce three types of relationships that can exist between tables. In order to follow along with this video, you should already have an understanding of foreign keys, primary keys, and the different types of joins that we've covered so far, particularly inner joins and outer joins. In the real world, we deal with things called entities, or anything that can exist that we might want to put into a database. An entity typically becomes a table for our purposes. The types of relationships between things in the real world in which we are interested is a one-to-one relationship, where one entity is directly related to one other entity. One-to-many relationships, where one entity may be related to many instances of another entity. And many-to-many relationships, where one entity may be related to many other entities, and each of those entities may be related to many of the first entities. We will see some examples of these, and they will become more clear to you. An example of a one-to-one relationship might be between houses and addresses of those houses. Every house has one address. That house isn't likely to move, and it can't be in two places at the same time. And each address has exactly one house. We don't have two houses at the same address. I know there are special cases for all of these examples, but we're talking in the general sense that should be reasonable for everyone. We could argue details about whether or not there could be two houses at the same address, or a house at two different addresses, but those are beyond the scope of what we do, so we will keep our examples simple and use things in the real world that are reasonable to understand. The one-to-many relationship might be with fish and lakes. If you have a given fish, it will live in only one lake. We'll assume that it doesn't jump from lake to lake or swim up a river to another lake. And that lake may have many fish. We'll assume that that lake doesn't have just one fish. That's a good example of a one-to-many relationship. One lake has many fish, and each fish has only one lake. You can make up a lot of these examples on your own and implement them as tables to see how this works, and I encourage you to log on to SSMS and experiment. The primary focus of these slides is the more complex of the three relationships, which is many-to-many. Our example that we will study in these slides is the example of Kroger stores and Pop-Tarts. Each Kroger store, which might be a row in a table, sells many flavors of Pop-Tarts, or they may sell none, or they may only sell one, but they certainly are likely to sell many. Each flavor of Pop-Tart is almost certainly sold in many different stores. It's unlikely that each flavor of Pop-Tarts will only be sold in one store. That would make a lot of sense. So store A might sell cherry and grape and frosted and plain, and the cherry Pop-Tarts may be sold in many different stores across the Kroger store chain. You can think of each store as being a row in a table, and each flavor of Pop-Tart as being a row in a table. You can think of a Kroger store in general as an entity, and a Pop-Tart flavor as an entity. Keep in mind, we're not talking about individual boxes of Pop-Tarts. We're just talking about the flavors that the Pop-Tarts may have. We're just interested in tracking what stores sell what flavors of Pop-Tarts and what Pop-Tarts are sold in which stores. The many-to-many relationship is special because it requires a third table. In order to implement this relationship properly, we need what is called an intermediate table, or a foreign key table, or just an extra table if you like. That table may not have much information in it. It may just have a primary key and 2 foreign keys. That could be as simple as 3 columns in the intermediate table. The 2 foreign keys are relationships or links or joins back to each of the entities that are participating in the many-to-many relationship. In our example then, the intermediate table will have a foreign key that points to a Kroger store in the store table, and a foreign key that points to the Pop-Tart flavor in the Pop-Tart flavor table. Here are our tables. I've created these in SSMS. I encourage you to log on to SSMS. There are Pop-Tart credentials provided for you on Blackboard. They will not be given here for security reasons. Look in the course documents folder and you will find credentials for the Pop-Tarts database. Use those credentials to log in. Expand the database called Pop-Tarts. Expand the tables folder and you will see 3 tables. The Kroger store table contains 1 row per store in our database. We can look at that table, right click, select top 1,000 rows. There aren't 1,000 rows, don't worry. There are 44 rows. We are interested in how this table is structured. Always take a few minutes to study the structure of the tables that you're dealing with. You may have to take more than a few minutes if they're complicated. We see that this table has a Kroger store ID, referring back to the naming conventions that we use in our databases. Since it has ID at the end of the column and the name of the column is the same as the table, then we know that that is the primary key, implemented as an auto number field. The store name, I will tell you, is the natural key. If you expand over here on the left, the columns folder, you can verify what I'm telling you. Kroger store ID is listed as PK, which is the primary key, and it doesn't show you that the store name is the natural key, but I can go ahead and add that since I have design privileges on these tables. Now I changed it to a key. Save that design. Refresh this folder. And the store name has now been set to the natural key, even though it doesn't show up that way in the column listing, but that's okay. The table also has an address field, a state field, and a comment field, which can all be left null. For the purposes of this demonstration, those fields are not important. We're primarily concerned about the ID column because it's the primary key and it will become a foreign key in the intermediate table. And for semantic reasons, so we have something to relate to, we're interested in the store names. But beyond that, the rest of the columns don't have a lot of importance to us at this point. That's the store table. We can look at the Pop-Tart flavor table. Remember, the store entities are stored in the store table. The Pop-Tart flavor entities are stored in the Pop-Tart flavor table. We can open the Pop-Tart flavor table, look at the columns, and we see that it's even shorter. It's an even smaller table. It has a primary key, which is our integer auto number field. It has the Pop-Tart flavor, which must be the natural key because it's the only other column. We can look at that table select 1000 rows. There are only 160 or 160 rows in this one. And you can look at the flavors. Some of them are kind of goofy. They were entered by students in a previous class. So this is meant to be a little bit silly. You can see the ID fields are incrementing integer values. Now these two tables need to relate to each other in a many-to-many configuration. One store can sell many flavors. One flavor can be sold by many stores. We need a way to do that that lets us have a many-to-many situation. So the way we set that up is with a third table called the intermediate table, the foreign key table, or there are other names it's also given, but I will typically call it the intermediate table. This table has 3 fields. It has its own primary key, which as you suspect is an integer value configured to automatically increment by the database engine. It has a foreign key called Pop-Tart Flavor ID and another foreign key called Kroger Store ID. From these names, you can surmise, you can guess that the Pop-Tart Flavor ID foreign key relates to the Pop-Tart Flavor ID primary key in the Pop-Tart Flavor table, and the Kroger Store ID relates to the primary key in the Kroger Store table. By naming these fields consistently according to the primary keys to which they relate in other tables, we have some semantic value that we can look at here. If you're not sure, if these names don't have any meaning to you, you could look at the design of the table, and remember you do have permission to look at the design, but you just can't make changes to it. Here's the intermediate table. Primary key, great. Primary key we can verify is set up as an identity value, and it is configured to increment by 1s each time we add a row to the table. No problem there. We've done that for the last few weeks in this course. That should be familiar to you. The foreign keys don't really, beyond the semantic value of the names, don't really tell you that they're foreign keys. So we can look and see under relationships that there is a foreign key called FK Kroger Store Pop-Tart. That's a name made up by SQL Server. We just leave it that way because it's a pretty descriptive name. And we can look at table and column specific, and we can see that the primary key is Kroger Store, with the Kroger Store ID being the value of that primary key. The foreign key is in the table we're currently looking at, and it is the same name, Kroger Store ID. So the names of the fields, when we choose them judiciously and wisely, tell us something about what those fields might be doing. Remember, we could call these X and Y if we like. We can call them anything we like, but a good name, a good descriptive name, goes a long way towards understanding what we're trying to accomplish. We can look at the other foreign key. You can see that SQL Server created a nice descriptive name for that field in the table. I'm sorry, for that foreign key in the table. We can look at the tables and columns. We can see that the primary key lives in the Pop-Tart Flavor table. The primary key is called Pop-Tart Flavor ID. The foreign key lives in the current table that we're looking at, and it is called Pop-Tart Flavor ID. Again, the names are the same. Just to make our lives easier, they don't have to be that way. That's an introduction then to the 3 tables that we need to implement the many-to-many relationship. Let's look at the data in the tables, because it makes our lives easier if we can relate to this data. In the Kroger Store table, let's note that 1022 is the Kroger Store ID, or the primary key for a store called Kroger. 1022. 1022. Now let's go to SSMS again. And let's open a new query window. And let's look in Kroger store for the record with the primary key of 1022. And we should see exactly what we just saw. There's the row in the table. If the store name is Kroger, the ID is 1022. So we verified what we just saw when we browsed the table. Now, let's look in the Kroger store Pop-Tart flavor, the intermediate table, for that same value in that same field. If I highlight this, it will only run that statement. I left out the where, my fault. There's 2 rows in that intermediate table with Kroger store ID 1022. What that means in the real world, in English, is that that store sells 2 flavors of Pop-Tarts. Here is the rudiment then of your many-to-many relationship. We are seeing that one store can be configured to sell multiple flavors of Pop-Tarts by adding multiple records to the intermediate table using that store ID. This is interesting then, but we don't know enough to do any real work. What we'd like to know then is what is Pop-Tart flavor 314 and what is Pop-Tart flavor 472. Those are primary keys in the Pop-Tart flavor table. Remember, this intermediate table has foreign key for the Pop-Tart flavors, foreign key for the Kroger stores, and then to get real information you have to join this intermediate table with the other 2 tables in the database to get names of stores and names of Pop-Tart flavors. This intermediate table has no use to the customer and not much use to us really until we join it with other tables to get useful semantic information. Let's flip back to the slides again. And in the next slide, we see that I provided the data for the Kroger store table, and you can verify that there are numerous stores in here. Each one has its own unique Kroger store ID, its own unique primary key. But keep in mind that doesn't tell us anything about what Pop-Tart flavors are sold in those stores. This is only store information, not Pop-Tart flavors information. And then here's the Pop-Tart flavor table actually. And in this table we see that each Pop-Tart flavor has its own unique primary key, its own unique flavor, and again there is nothing in here defining what flavors are sold at what stores. We have a store table, we have a Pop-Tart flavor table. They are not related except through that intermediate table. They don't say anything about the other. Each says nothing about the other until we implement the intermediate table. On the next slide, here is a visual representation of the connection between the 3 tables. Remember, we consider the tables to represent entities or things in the real world, and the things in the real world in this case study are Kroger stores and Pop-Tart flavors. Flavors exist conceptually. You can't really see a strawberry flavor, you can't really see a cherry flavor, but they are in the real world and people do understand what they mean even if they can't see them. And then the other entity are physical concrete things referred to as Kroger stores. And it's very useful then to implement this many-to-many relationship by putting in the intermediate table. Here's the data in the intermediate table. As we saw earlier, we saw an example where we filtered on Kroger store ID as 1022, but here's the full-blown table, and you can see that there are numerous records in this table allowing us to create a many-to-many relationship between the two entities. If we flip back to SSMS, we can look at the contents of that intermediate table just like it is in the slide. We can scroll down. In the next video, we will continue with this concept and we will join the three tables together to produce useful results.